To understand option A in this particular question, we must first recall the following. Let us imagine that a particle travels from a point P to another point Q. Now it is possible for the particle to travel in a straight line in the same direction, that is from P to Q. However, it is not compulsory that the particle does so. So for example, in this particular case, let us imagine that the particle travels along a curved path and finally reaches point Q. Now let's try to figure out the relationship between the distance covered by the particle and the magnitude of the particle's displacement. Clearly, the magnitude of the displacement is the length of this particular line segment PQ. On the other hand, the distance covered by the particle is the length of this entire curve, and let's imagine that we straighten it out. Obviously the length is going to be larger than length PQ. So if we go back to this relation, clearly the distance covered in this case will be larger than the magnitude of the displacement, and this will always be the case excepting for one particular case, and that case of course occurs when the particle actually travels in a straight line from P to Q without changing its direction. Clearly, when this happens, the distance covered by the particle is length PQ, which is of course equal to the magnitude of the particle's displacement. So in this special case I get an equality sign, and in all other cases, as discussed previously, I get a greater than sign. So I combine these together and I write it as follows. The distance covered by a particle will always be greater than or equal to the mod of the displacement. This also covers the trivial case when the particle doesn't move at all. In that case, the distance covered by the particle is equal to 0 because it's stationary, and naturally the mod of the displacement is also equal to 0 because the particle doesn't move from its starting position. So in that case you get an equal to sign, which is covered in this general inequality greater than or equal to sign. So the general rule seems to be, whenever a particle moves, or even in case it doesn't move, the distance covered by the particle will always be greater than or equal to the magnitude of its displacement. Now just imagine that I divide each side of this inequality by the time interval delta t in which the displacement occurs. Delta t can't be negative, we know that. It's always a positive quantity. Now the left hand side becomes the average speed of the particle, and on the other hand the right hand side can be written as the modulus of the displacement. I can take the delta t term inside the mod sign because I know it's not negative, and I also know it's not 0. I'm not trying to divide by 0, which is absurd. And the displacement divided by delta t is obviously the average velocity of that particle during the time interval delta t, and I've got a mod sign around it, and so what I've got on the right hand side is essentially the magnitude of the average velocity. So I just move this term over here, and this particular sign I'll put it over here. My result is the average speed of a particle will always be greater than or equal to the magnitude of its average velocity, which of course solves option number, because this particular inequality tells us that the average speed of a particle during a certain time interval cannot be less than, can never be less than the magnitude of its average velocity during that same time interval, and hence option A is true. Now we can turn to option B, and in this particular option the statement given is that it is possible to have a situation in which the modulus of dv bar by dt is not equal to 0, but d of mod v bar by dt is equal to 0. Note that the option uses the word possible. It doesn't use the word compulsory, doesn't use the word necessary, which means that if we can even show as an illustration one case where this particular thing happens, then of course the option will be proved to be correct. Now to do that, it is necessary to understand the difference between the term modulus of dv bar by dt and d modulus of v bar by dt. They look the same, but they are two entirely different terms. To investigate the first term and to understand it well, look at the term which is inside the mod sign. So dv bar by dt, this particular term, is clearly the instantaneous acceleration of the particle. So this is a bar, and it basically means that the modulus of a bar, that's what we are talking about, is not equal to 0. So I'll just rewrite this particular thing. A bar, the modulus of that, is not equal to 0, is basically what this entire statement means. On the other hand, this second expression d mod v bar by dt looks a bit like the first expression, but with a major difference, that is the mod sign has been brought inside. It's not outside, but it's inside. It covers v bar. So as usual, we have to start analyzing this expression by starting from the innermost thing. So the innermost thing is of course v bar, the instantaneous velocity, but just outside that I've got a mod sign, and we all know that the mod of the instantaneous velocity, that's the magnitude of the instantaneous velocity, that's nothing but the instantaneous speed, and d of speed by dt means the rate at which the speed changes or is changing with respect to time. And to understand this entire equation, note that this particular rate at which speed changes with respect to time is equal to 0. Now whenever the rate at which something changes with respect to time is equal to 0, it means that that thing doesn't change at all. Hence this statement in simple language means that the speed of the particle is a constant. So in simple English, the entire statement is, it is possible to have a situation where the magnitude of the acceleration is not equal to 0, but the speed is equal to constant. Now we can even simplify that further. When you say that the magnitude of the acceleration is not equal to 0, it essentially means that the acceleration is not equal to 0 bar. So it's possible to have a situation where the acceleration is non-zero or non-zero bar, but the speed is not changing, that is, it is a constant. Now if you look at this first statement, the acceleration is not equal to 0 bar. Now that would mean, of course, that the velocity is changing. So the final simplification of this statement is, it is possible that the instantaneous velocity is changing, but the speed of the particle is a constant. It never changes. Now let's take an example where a particle is traveling from a point P to a point Q, and let's say that the particle moves along a straight path like that. And in this case, if the particle, of course the particle may start to the left of P and it may go beyond Q, so maybe PQ is a part of the entire path. Now if the particle travels with a uniform speed during the journey from P to Q, and the particle never ever changes its direction. It simply goes towards the right continuously. Now that would be a case where the speed is uniform and the velocity also doesn't change. So this is of course not an example, not the example that we are trying to look for. But now let's try to change the example. Let's imagine that instead of moving always from left to right, maybe the particle is moving along a curved path like this, which passes through P and also passes through Q. Now maybe the particle is moving in the general direction from left to right throughout. Now imagine that the particle moves at a constant speed. For example, this could be a road, and the particle could be visualized to be a car which is moving at a constant speed. Now clearly, if you look at the direction of motion of the particle, since it is always in the direction of the forward tangent, the direction of motion is changing in this particular journey, which would automatically imply that the velocity changes, because the direction of the velocity changes. In fact, there are two ways in which the velocity can change. One is the change in the magnitude of the velocity, that is, when the speed changes, we say that the velocity changes. The other way could be the speed doesn't change, the magnitude of the velocity doesn't change, but the direction changes. In either case, we say that the velocity changes. Of course, there could be a third case in which the magnitude as well as the direction of the velocity changes, but we are not interested in that case currently. We have got a situation where the speed, that is the magnitude of the velocity, doesn't change during the journey from P to Q, but the direction of the velocity definitely does change, and hence we have got a nice example. It's an example of the velocity changing but the speed not changing at all, the speed being a constant. And this one example is sufficient to show that option B is true or correct. Now let's look at option C. In this option, we are given the data that the average velocity of a particle during a certain time interval is 0. Of course, since it's a vector, what they mean is 0 bar during a certain time interval. And the statement is as follows. It says it is possible for the particle's velocity to never be equal to 0 bar in this particular time interval. Now when we simplify this statement, if V bar is never equal to 0 bar in a certain time interval, it basically means that the particle never stops even for an instant during that time interval, which essentially means that the particle continuously moves during that particular time interval. So in simple language, the statement given is as follows. It is possible for the average velocity to be equal to 0 bar for a continuously moving particle. The answer to this question is that it is possible. The option is true, and the example that we can cite in support of our claim is the following. Consider a particle which is traveling along a circle, something like this. So the particle moves along a circle, and in particular let it move with uniform speed. So that's a type of circular motion called uniform circular motion. So you can imagine that the particle travels in the clockwise direction. So in uniform circular motion, the particle has to continuously keep on traveling in the clockwise direction in this example with its speed never changing. You can even consider its speed to be 5 meters per second. So maybe the particle, when it's over here, it's moving 5 meters per second in that direction. When it's over here, again it's moving at 5 meters per second in that direction, and likewise when it is here, it's moving at 5 meters per second in that direction. Now imagine that the particle completes exactly one revolution, that is, the particle comes back to its starting point. If we consider what is the displacement of the particle, s bar, clearly since the particle has reached its starting point, the displacement must be equal to 0 bar, and hence the average velocity of the particle during this particular time interval is the displacement upon the time taken. So it's going to be 0 bar divided by whatever time was taken to complete a revolution, and clearly the average velocity is equal to 0 bar. So we have an example where the average velocity of a particle is equal to 0 bar, but if you look closely at the example, you realize that the particle was continuously moving throughout the process. So it is possible for the average velocity to be 0 bar for a continuously moving particle. The option C is clearly true. Now in option D, we are given that a certain particle is moving along a straight line, and in a certain time interval the average velocity of the particle is given to be equal to 0. Now when the average velocity of the particle is stated to be 0 bar, of course it means that the displacement of the particle divided by the time interval in which the displacement occurs is equal to 0 bar, and that automatically means that we are talking about a time interval in which the particle's displacement is 0 bar. So the particle must return to the starting point, which is the meaning of saying that the displacement is equal to 0 bar. So let's try to give an example. Let's say that the particle is moving along this straight line, and maybe the particle is moving from left to right initially, and when the particle passes through this point, which I'll call P, that's the time that you start your stopwatch. So that's the beginning of the time interval delta t. Now let's say that the particle continues to move right like that. Remember, after a time delta t, we have to find the particle back at point P. Clearly the particle has to reverse its velocity at some point of time, and that's because without reversing its velocity there's no way that it can reach P again, because it's moving on a straight line. So as the particle moves ahead, maybe it slows down, and at a certain point it actually stops momentarily maybe, and then its velocity becomes leftward. So now the particle travels leftward like that, and finally it comes back to point P. So this is a situation in which the average velocity of the particle is 0 bar, and at this particular point the particle's instantaneous velocity was equal to 0 bar. Now if you read the question, it says that it is possible that the particle's instantaneous velocity is never equal to 0 bar, during this particular time interval. Now if you look at our example, although the average velocity of the particle is indeed equal to 0 bar during the given time interval, its velocity does become 0 bar at this particular point, and hence the conditions of the question are not fulfilled by our example. Now that's because we assumed that when the particle was traveling towards the right, as it approached this particular point Q, it slowed down. At point Q, it stopped momentarily, and then it gathered speed traveling in the opposite direction. So it reversed its velocity and finally managed to reach point P once again. Now, is it possible for the particle to stop at point Q without slowing down and again speeding up? Just to give a numerical example, just before reaching point Q, let's imagine that the particle is traveling right at a velocity of 5. Now I'll assume that the rightward direction is the x-axis. The particle may be moving along the x-axis. So 5 I cap meters per second is the velocity just before reaching point Q, that is just to the left of Q. So maybe the particle is somewhere over here, and in a time interval dt, when the particle actually reaches Q, what we would like to happen is that the particle has got a velocity of, just let's put a figure over here, minus 2 I cap meters per second. So what I'm trying to say here is the particle just before reaching Q had a rightward velocity 5 I cap meters per second, and when it reached Q in a time dt, its velocity became minus 2 I cap meters per second. Now this would be an example where the particle's velocity never becomes 0, because even at point Q, where it was 0 bar in the previous example, the particle's velocity just before Q is 5 I cap meters per second, and in a time interval dt, which is arbitrarily small, you could reduce dt indefinitely. Just after that time interval dt, the particle's velocity suddenly, before you can blink your eyes, has become minus 2 I cap meters per second. So this is an example where from 5 I cap meters per second, the velocity suddenly became minus 2 I cap meters per second without becoming 0 bar in between. Now the question is this phenomenon possible? And we have to actually investigate what's happening in this time interval dt to answer this question. So let's try to find what is the instantaneous acceleration of the particle during that time interval. Now the instantaneous acceleration is the limit of the average acceleration, so it's limit of delta v bar by delta t, and of course the time interval has to tend to 0, then it's called the instantaneous acceleration. Now let's try to figure out what the instantaneous acceleration is. Now the change in the velocity, this term, is the final velocity minus the initial velocity. So I'll just write the limit again, the limit as delta t tends to 0. The final velocity is minus 2 I cap meters per second, and the initial velocity, which we have to subtract, is 5 I cap meters per second. So this gives me minus 7 I cap meters per second in the numerator, and that of course is divided by delta t. Now if you allow delta t to tend to 0, what it means is delta t is so small that you cannot think of a smaller number. As this value becomes smaller and smaller and smaller, this fraction, which is 7 divided by delta t, becomes larger and larger and larger, and as delta t approaches 0, 7 upon delta t would actually approach infinity. So what is the acceleration? The instantaneous acceleration in the time interval dt under consideration is the limit of this term as delta t tends to 0. So obviously it's going to be minus infinity I cap meters per second square, which means we have a situation of infinite instantaneous acceleration just before point Q is reached. In fact, having infinite instantaneous acceleration at least one point seems to be the only way that the conditions of the question can be fulfilled. But the question clearly states that infinite accelerations are not allowed, and hence it is not possible to meet the conditions of the question. What we are essentially saying here is that if the particle has to reverse its velocity, which it must if it has to reach P again, then there must be some point Q where the instantaneous velocity is equal to 0 bar. The particle must essentially slow down just before Q, stop momentarily at Q, and then gather speed traveling in the opposite direction. It is not possible for a particle which is moving along a straight line to return to a point P without its velocity becoming 0 bar at some point Q. It might be possible, of course, if infinite accelerations were allowed, but they aren't in the question, and so obviously this particular option is wrong. Now, something about infinite accelerations. Is it practical for us to assume that infinite accelerations are not allowed? The answer is yes. The condition given in the question is not by accident. Remember, Newton's second law of motion states that the net force acting on a particle is its mass times its acceleration. And if infinite accelerations were allowed, for example here this is minus infinity times I cap, then clearly the force which would generate such an infinitely large acceleration has to be of infinite magnitude, which is not possible in practice. It's not possible to have an infinitely large force. Hence, even in practice, it is not possible for a particle to have infinitely large accelerations. In short, the answer to this question, this sub-question, is it is not possible. So the statement is false.